In this presentation, I will be explaining the different application of operation amplifiers. Let us consider the first application, scale changer, or as well as sometimes it can operate as an inverter. It is a op-amp circuit in which you are giving the input to the inverting terminal. Vi is given the input terminal, and output voltage is between the output voltage and this non-inverting terminal RF. We have feedback resistance RF, and we have equal to R1 is there, and this is a compensating resistance, which is normally it is the parallel combination of R1 and RF, R1 parallel with RF. As in practical circuit, in order to compensate the bias, input bias current, you have to connect a resistance R compensation resistance, which is equal to parallel combination of the input resistance R1 and the feedback resistance RF. Coming to the inverting, and this is an inverter amplifier configuration. The gain of the inverting amplifier configuration is given by minus RF divided by R1, or the output voltage is given by minus RF divided by R1 times the input voltage. Now, if you make RF divided by R1 equal to a constant K, we are replacing RF by R1 as a constant K, and that's called a scale changer. Then output voltage is equal to that K times the input voltage, or minus K times input voltage, because a negative sign is there. V0 equal to minus RF by R1 into Vi, or output voltage equal to minus K times Vi, or this K output voltage is a scale version of the input voltage with a inversion, minus sign is there. Therefore, if K equal to 1, as an example, this is called a scale changer. If you substitute, you can make K equal to 2, 3, whatever you can make it. Then output voltage, the scaled amplified version of the input voltage with a inversion. But if K is made equal to 1, if you make the K equal to 1, then V0 equal to minus Vi. If K equal to 1, the circuit is called an inverter, because output voltage is equal to minus Vi, or V0 equal to minus. The output voltage is the inverter version of the input. That's called the inverter. Then the output is 180 degree out of phase with the with respect to the input voltage, and it has got the same magnitude as the input voltage, but there's a 180 degree phase shift is there. That's called an inverter. The scale changer means you can change this scale K value RF by R1. You can change the magnitude of the output voltage with a negative voltage, or with a 180 degree phase shift. And if you are making RF by R1 equal to unity, it is working as an inverter. And in that inverter, output magnitude is same as the input magnitude, but there's a phase shift. And the RComp is the compensation resistance, which is to compensate against the input bias current, and which is equal to the parallel combination of the this R1 and RF. Actually, that will be parallel combination of the input resistance, that is R1, and the feedback resistance RF. Let us see the second application as a summing amplifier. In summing amplifier, let's say inverting summing amplifier and non-inverting summing amplifier is there. This is an inverting summing amplifier in which we want to sum up these voltages V1, V2, V3. These are the voltages to be summed up, and output voltage is the summation of this input voltage with a weighted gain is there, but there's an inversion is there. That's called inverter or inverting summing amplifier, in which is an op-amp circuit in which here at the negative or inverting input, you are connecting the input signal V1, V2, V3 through resistance R1, R2, R3, and feedback resistance RF is connected, and that is between the output and this inverting terminal of the op-amp. And as we have seen in the scale changer, there is a compensating resistance. This RComp is equal to, actually, it is the parallel combination of R1, R2, R3, and RF. That is input resistance, if you're looking from this one, is equal to R1 parallel with R2 in parallel with R3. And to that one, RF is to be added in parallel, so that RComp equal to R1 parallel with R2, parallel with R3, parallel with RF. This is the compensating resistance. Therefore, this is a circuit diagram of a inverting summing amplifier. Let us analyze this one. Now, V1, V2, and V3, these are the input voltages. V1, V2, V3 are the input voltages. R1, R2, and R3 are the input resistance. So we are externally connecting R1, R2, R3 at the input side. And assuming the open loop gain of this one, but we are assuming that open loop gain is infinity, and input impedance is infinity. Input impedance of the op-amp is infinity. Open loop gain is infinity, as well as the input resistance is also infinity for the op-amp. This is ideal case. And the input bias current is also assumed, because and bias current will be very in microamperes. That is also we are assuming. In ideal case, that is assuming 0. For three things we are assuming: the input impedance is infinity, open loop gain is infinity, and this bias current is very small. And under that condition, since the current is very small, this ground voltage is same as this voltage at the non-inverting terminal. Or we can see that one, the voltage at the inverting terminal is same as the non, that's called the virtual ground, and that is same as this ground voltage. Since the voltage drop across is very small, because bias current is very small, and the voltage at the point A, that is same as the ground voltage. The voltage at the point A is same as the ground voltage, 0 voltage. Now, if you apply the Kirchhoff's current law to the point A here, that is input here, non-inverting terminal is grounded, that is here non-inverting terminal is at the ground potential, because the non-inverting terminal is ground, because this ground potential is coming at this point, and that is same as this potential. This is grounded. Now if you apply the Kirchhoff's current law to this node A, we can get it as V1 by R1 plus V2 by R2 plus V3 by R3, that is the current coming towards the junction, that is that plus this, that is V0 by Rf equal to 0 plus V0 divided by Rf equal to 0. We are applying the Kirchhoff's current law to this node, and the total current coming towards this junction equal to this current plus this current plus this current, V0 minus V0 divided by Rf, because this we are assuming as 0 voltage. Therefore, if you group this, the output voltage, now output voltage is equal to, if you group it that one, Rf divided by R1 into V1, of course minus sign is there, minus into Rf by R1 into V1 plus Rf by R2 into V2 plus Rf by R3 into V3. This is the output voltage at this one in terms of the voltage V1, V2, V3 and the feedback resistance Rf and R1, R2 and R3. That is meaning that output voltage is an inverted weighted sum of the input voltage. It's a weighted sum because Rf by R1, Rf by R2, Rf by R3, these are the weight. And summation is there, there's an inversion is there. That is why output is an inverted weighted sum of the input voltage. Continuing the inverting summing amplifier, same circuit diagram in which here V1, V2, V3 are the input voltage, V0 is output voltage, V0 is given by inversion is the minus Rf by R1 into V1 plus Rf here minus outside is the plus Rf by R2 into V2 plus Rf by R3 into V3. That is the output voltage in this case. Now in certain cases we assume that R1 equal to R2 equal to R3 equal to Rf, which is equal to R. All these resistors are equal. If you are assuming that, if you substitute here, you will be getting it is output voltage equal to, if R1 equal to Rf, it is equal to 1. Similarly, R2 equal to Rf, 1. Rf equal to Rf equal to, both are equal, means of 1. For output voltage equal to minus of V1 plus V2 plus V3. Therefore, output voltage is a summation of the input voltage with an inversion, minus of V1 plus V2 plus V3. Now, instead of this equal value, if you assume that R1 equal to R2 equal to R3, which is equal to 3 times Rf, which is equal to 3 times Rf. If you substitute that same thing here, if you take it as here, it will be getting, it is equal to, what is Rf, if you substitute in the, here we will be getting, it is equal to minus of V1 plus V2 plus V3 divided by 3, because R1 equal to 3 times Rf. Therefore, here it will be getting 3 times Rf, means here it will become 1 by 3, 1 by 3, 1 by 3, or it is equal to minus of V1 plus V2 plus V3 divided by 3, or output voltage is equal to minus of V1 plus V2 plus V3 divided by 3, or we can say that it is the average of the output voltage with an inversion. Therefore, output is an average of the input signal with the inverted output. Therefore, if you make R1 equal to R2 equal to R3 equal to 3 times Rf, you will be getting the average value of this voltages. The average value of the voltage will be getting with the inversion is the minus of V1 plus V2 plus V3 divided by 3. This was the second case. And here, another thing is that to find out this R-com, normal practice is that we will be finding out what is the input impedance. That is, by grounding this one, what is the impedance looking from this one. Therefore, R1 parallel with R2 parallel with R3. That is the input impedance looking from this one. To that one, Rf will also be coming in parallel. Therefore, it is equal to effective input resistance equal to R1 parallel with R2 plus in parallel with R3. That's the effective input resistance. and RComp is getting but this effective input impedance or resistance that is in parallel with RF. Therefore, RComp, compensation resistance that is to be connected externally in a practical circuit, is equal to R1 parallel with R2 parallel with R3 in parallel with RF. Therefore, this is a practical circuit of inverting summing amplifier. Summation is the, of course, there's an inversion is also there. We are giving the input to the inverting terminal. That is why there's an inversion. There's a problem like design an adder circuit using operation amplifier to get the output voltage V0 equal to minus of 0.1 V1 plus V2 plus 10 times V3. This is the voltage equation you want to get the output voltage here. Therefore, it is actually, it is a minus is there, it is a inverting, summing amplifier. Therefore, that is why we are giving the input at the inverting terminal. Therefore, here V1, V2, V3 and of course R1, R2, R3 and RF is taken, and the first weight is given as the weightage is here 0.1, here it is equal to 1 and here equal to 10. And this weightage is, as per this equation, V0 is given by, the V0 is given by minus of RF divided by R1 into V1 plus RF divided by R2 into V2 plus RF divided by R3 into V3. Therefore, here the weightage RF by R1 equal to 0.1. Therefore, will be, in order to get that one, we have to choose the value of RF, R1, R2 and R3. As an example here, if you take this RF here, that as this example, take RF equal to 10 kilo ohms. If you are, that is an example, you can take any value, appropriate value. Just I am taking as feedback resistance equal to 10 kilo ohms. And similarly, R1 I am taking it as RF divided by 100 kilo ohms. And R2 I am taking it as 10 kilo ohms. And R3 I am taking as 1 kilo. This is 1 kilo, this is a 10 kilo, this is a 100 kilo, and this is a 10 kilo. This is like this I am taking. Now, if you apply this one, we can see that one V0 equal to minus of 10 divided by, this is 100, 10 divided by 100, 10 kilo ohm divided by 100 kilo ohm into V1 plus 10 divided by 10 kilo ohm into V2 plus 10 divided by 1 kilo into V3, or here if you substitute here 10 by 100, 0.1 V1 plus V2 plus 10 V3, minus sign is there. Therefore, like that one, if you connect this resistance value with these values like 10 kilo ohm R1, R2 100 kilo ohm and R3 10, R1 RF equal to 10 and this is equal to 100 and this is equal to of course 10 and R3 equal to 1 kilo ohm, then you will be getting the output voltage equal to in this equation, that is V0 equal to minus of 0.1 V1 plus V2 plus 10 V3. Therefore, that is the way in which you can implement this realizing this voltage equation. Output voltage equal to 0.1 times V1 plus V2 plus 10 times V3, of course, with an inversion. Therefore, that is why inverting amplifier with a summation, inverting summing amplifier. Second summing amplifier is called non-inverting summing amplifier, in which we are giving the input signal to the non-inverting terminals. Previously, we gave the input signal to the inverting terminal. But here we are giving to the non-inverting terminal like V1, V2, V3. These are the signals to be added through a resistances R1, R2, R3. Feedback resistance equal to say RF is there, and the input side there's a resistance R is there. There's an input resistance R at the. It is a non-inverting terminal, non-inverting amplifier. You say resistance is grounded through a resistance R. Therefore, this is a non-inverting summing amplifier. Same as the previous case, you have to analyze this one and you have to find out the equation for the output voltage. Therefore, a summer that gives non-inverted sum is called a non-inverting summing amplifier. Its output is a non-inverted version of the summation of this voltage. Therefore, again, in order to do this one, the nodal equation at the node A we have to apply. We have to apply the node equation at this point. What is the nodal equation at this point? Therefore, in order to find out the node equation at this point, here V1 minus VA divided by R1 plus V2 minus VA divided by R2 plus V3 minus VA divided by R3, that is equal to the input current to this one. But since the input current equal to 0, that can be equated to 0. Therefore, summation of this current that can be equated to 0 because the input current to the op amp equal to 0. Now, reducing this equation, because input current equals 0, that's current. Reducing this equation, we can get V1 by R1 plus V2 by R2 plus V3 by R3 equal to V0 taken outside, other side, V0 into 1 by R1 plus 1 by R2 plus 1 by R3. Or the volt, not V0, it's a VA, not V0, sorry, this is a VA. This is a voltage, V0, say V1 minus VA, that is this voltage, V1 minus VA. So for the voltage at this point, VA, V0 is this voltage. Here we are finding out what is the VA. So for the voltage at VA is given by, what is that, V1 by R1 plus V2 by R2 plus V3 by R3 divided by 1 by R1 plus 1 by R2 plus 1 by R3. Therefore, this is the equation to find out the voltage at this non-inverting terminal VA. Once you get the non-inverting voltage VA here, the output voltage is given by, as a non-inverting amplifier, V0 equal to 1 plus RF divided by R into VA. 1 plus RF divided by R into VA. Therefore, the output voltage is given by op amp with the two resistance RF and R, constitute, that it is equal to 1 plus RF divided by R into VA. And substituting for this VA, whatever you found out, this VA is substituted in this equation. Therefore, the output voltage V0 can be written as 1 plus RF divided by R, say, non-inverting amplifier gain, 1 plus RF divided by R into whatever the voltage coming at this point, VA, which is equal to this one, V1 by R1 plus V2 by R2 plus V3 by R3 divided by 1 by R1 plus 1 by R2 plus 1 by R3. Therefore, this is the output voltage. That is called, this is called non-inverted weighted sum of the input voltages, inputs. Non-inverted weighted sum of the input. That is a non-inverting summing amplifier here. And if you make R1 equal to R2 equal to R3 equal to R, if you make R1 equal to R2 equal to R3 equal to R, and here the feedback resistance RF equal to again R, that is R1, R2, R3 equal to R, which is, and RF equal to twice R. Now if you substitute it in this equation, same thing here, then you will be getting, then output voltage is equal to V1 plus V2 plus V3. You will be getting the output voltage, the summation of the voltage V1 plus V2 plus V3, provided R1 equal to R2 equal to R3 equal to R, and feedback resistance RF equal to 2R. The next application is a subtractor. You can subtract two signals, two voltages, like V1 and V2 are the signal that is to be subtracted. And here the resistance is, this is a op amp which is connected, and V1 is connected to the non-inverting terminal, and inverting terminal we are connecting the V2, and through two resistors, voltage divider resistors R and R, both are equal, and here also feedback resistance R, and this is equal to R. Therefore, the output voltage is nothing but the difference in voltage V1 and V2. You can prove that one. The output, this is a subtractor, whatever the signal given V1 minus the signal V2, that is the output voltage with this, provided all these resistances are equal, R, 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 R. Now, in order to prove that one here, we have to see what is the output voltage when both inputs are applied, V1 and V2. Therefore, the output voltage can be derived using the superposition theorem. Best theorem is the superposition theorem. When there are more than one inputs, you can apply the superposition theorem. For example, in this case, when both V1 and V2 is applied, what is the output? Now to find out that one, first assume that V1 is present, then V2 you will be grounded, and you will be seeing what is the output voltage. Let us make as V01. Second case, you will be grounding V1 and you will be applying V2 there, and corresponding output is equal to V02. When V1 and V2 both are present, the output voltage is given by V01 plus V02. That is called the superposition theorem. In the same way here, if V01 is the output corresponding to the input V1 alone, means V2 is grounded, and V02 is the output corresponding to the input V2 alone, then the output when both inputs are V1 and V2 are present, are applied, then output voltage equal to V01 plus whatever the output we are getting the first case, V01 plus V02. That is the output when both inputs are present. Now to find out the V01, first we are applying the voltage to V1 and V2 is grounded. This point is grounded, we are applying the V1. When we are applying a voltage of V1 here, the voltage at this point, non-inverting terminal is given by V1 divided by R plus R into R, or that is nothing but V by 2. This voltage is equal to V by 2. Then this is grounded also. Therefore, then this is working as an non-inverting amplifier. Then what is the output corresponding? V01 equal to 1 plus R by R into whatever the voltage here. 1 plus R by R into V2 by 2, or here get 1 plus R by R into V1. This is a V1 and this is a V2. It is equal to, here we will be getting V1 by 2, V1 divided by R plus R into R. This is V1 by 2, and then corresponding output voltage V01 is given by, which is equal to V1 by 2 into 1 plus R by R, which is equal to V1. That is when V01. Now to find out V02, that is when V2 is present, V2 alone is present, V1 is grounded, and here you are applying the voltage V2. Then since it is grounded, this potential is being grounded, then it is simply a inverting amplifier. Output voltage V02 equal to minus R by R into V2, minus R by R into V2 or V2. Therefore, V01 equal to V1 and V02 equal to minus V2. Or when both inputs are applied, V1 and V2 are applied, the total output V0 equal to V01 plus V02, or meaning that V1 minus V2. The output voltage when both inputs are present, V1 and V2 are present, can be obtained as per the superposition theorem equal to V01 plus V02, or V01 equal to V1 and V02 equal to minus V2, or V1 minus V2. That is, whatever the signal you are giving V1, that is subtracted from the second signal V2, that is available at the output. Therefore, this is a subtractor, simple subtractor, in which you can subtract the two signal by this method. In this one, of course, we are applying the superposition theorem. That is, when more than one input signals are coming, you can apply the superposition theorem. Now let us another application in which both adder and subtractor are there. It's adder subtractor, and that is why we will be giving the input signal to both the non-inverting input, inverting input as well as non-inverting inputs, and we can apply the superposition theorem when there is more than one input, as I told you the previous slide. That is, in this case there are four inputs. Here you are getting the V1, V2 and V3 and V4. There are four inputs are there. When what is the output when all the inputs are coming? For that one you have to apply the superposition. That is, first we are assuming that V1 is present, and what is the corresponding output voltage? That is, the output voltage when V1 is applied, then we are making V2, V3 and V4 all are grounded, and the corresponding output voltage equal to V01. Similarly, second case, when V2 alone is applied, you are applying the V2 alone. The V2 alone is applied. Here V2 alone is applied, and this is a V1, and V2 is alone is applied. As V2 alone is applied, you are making V1, V3, V4 all are 0, and the corresponding output equal to V02. And the third case is that when only V3 is applied here. When V3 is applied, all others are grounded, and meaning that here V1 and V2 and V4 all are grounded, and the corresponding output you are getting V03. And the fourth case is that output is applied, only P4 is applied to the fourth input is applied, and all others are grounded, and you can see that V1 equal to V2 equal to V3 equal to 0, and the corresponding output equal to V04. Therefore, these are the outputs when on one of the input is applied, remainings are grounded, V01, V02, V03 and V04. When all the inputs are applied, V1, V2, V3, V4, the corresponding output voltage V0 is given by the sum of this one, V01 plus V02 plus V03 plus V04. That is a superposition theorem. Therefore, the output voltage when all the inputs V1, V2, V3 and V4 are applied, it is equal to V0 equal to V01 plus V02 plus V03 plus V04. That is, in that way you can find out the summation of all these signals using superposition theorem. Continuing this adder subtractor circuit, this is adder subtractor circuit. Here the signals, these signals are applying to the non-inverting terminal, and these signals are applied to the inverting terminal. And that is, here we are V1 and V2, and here V3 and V4, and here all the resistance are equal. We are connected all the resistance equal values, and feedback resistance as well as all these resistance are all are value of R. Now we have to analyze what is V0, what is V01. Only when V1 is present, what is the output voltage V01. In order to find out that one, we are grounding all this. We are grounding, V2 is grounded, V3 is grounded, and V4 is grounded. Let it be like this one. The circuit is like this one. It comes to like one, and only the input V1 is applied. Or the corresponding circuit can be redrawn as like this one, applying, because this is grounded, and what is this Thevenin's equivalence, applying Thevenin's equivalent circuit here. The corresponding voltage at this point is given by this voltage V1 divided by R into R, or V1 by 2. This voltage equal to V1 by 2, and the equivalent resistance equal to R parallel with R into R divided by R plus R. It is equal to R by 2. Therefore, so R into R divided by R plus R, or R squared divided by R, that is equal to R by 2. Therefore, this equivalent circuit is equal to V1 by 2 into R by 2, and this is a feedback resistance R is there, and this circuit is now, then corresponding output voltage can be found out. Is an inverting amplifier configuration. Output voltage is given by, it is equal to minus R divided by R by 2 into V1 by 2, minus R divided by R by 2 into V1 by 2, or that's equal to minus V1. Therefore, the V01 is equal to minus V1. In the same argument, when V2 is present, you are grounding all other inputs. In the same method, you can get as V02 equal to, same method here, same argument, you will be getting it is equal to minus V2, or V02 equal to minus V2. When V2 alone is present, all others are grounded. Same way you can calculate what is the output, and then you will be getting it is equal to minus V2. Therefore, V01 is only when V1 is present, all others are grounded, and V02 is V2 is present, all others are grounded, and V01 you will be getting minus V1, and V02 equal to minus V2. Now coming to the other two things, V03 and V04. In order to find out V03, all except 3 are grounded. This is grounded, as well as this is also grounded. Therefore, equivalent circuit is like this one. It is like this one. This is grounded. Therefore, here these are coming in parallel. Both are grounded, means they will be coming parallel. That is equal to R parallel, which means R by 2. And this is equal to R. Therefore, here V3 is coming here, and V3 is here. There's a resistance R is there. Again, these are both are, these are grounded, means R and R parallel. It is equal to R by 2. Now, what is the voltage at this point? If you calculate the voltage at this point, whatever this voltage V3 divided by R plus this equivalent is equal to R by 2. V3 divided by R plus R by 2 into R by 2, or V3 divided by, here V3 divided by R plus R by 2 into R by 2, or you will be getting it is equal to V3 by 3. This voltage is equal to V3 by 3. The voltage at the non-inverting terminal is equal to V3 by 3 by this equation. Once this voltage is equal to V3 by 3, this is a non-inverting amplifier. Output voltage is given by whatever this voltage into 1 plus this resistance divided by R by 2, this resistance, or 1 plus R by 2 into this V3 by 3, or 1 plus R divided by R by 2 into whatever this voltage means, it is equal to V3 by 3, or that you will be getting it is equal to V3. This voltage equal to V3. Therefore, V03 is equal to V3. Similarly, V04 also you can find out the same argument. You will be applying the voltage to this one. All others are grounded, and the same equivalent circuit you can find out what is V04, which is nothing but it is equal to V4. V04 equal to V4. Therefore, we got V01 minus V1, V02 minus V2, V03 it is equal to V3, and V04 it is equal to V4. Therefore, when all the inputs are applied, the output as per the superposition theorem, it is equal to V01 plus V02 plus V03 plus V04, and that is equal to the output voltage V0 when all the inputs V1, V2, V3 and V4 are applied, which is equal to V0 equal to V01 plus V02 plus V03 plus V04, which is equal to, here
what we getting is V3 plus V4 minus of V1 plus V2. Or whatever the voltage coming here, that is getting added, and whatever voltages are coming here, that is getting subtracted. That is why it is called adder subtractor. Here V1 and here V3 and V4 are coming, they are getting added, V3 plus V4, and here V1 and V2, that is added and subtracted from this one. So that output voltage is equal to addition of this voltage minus this is being subtracted. Therefore, that is the output voltage. That is what is called adder subtractor. Therefore, in the op-amp circuit, that involves the addition of the voltages. Similarly, the subtraction of the voltages. That is called the adder subtractor circuit of op-amp.